All right. Okay, let's get started. If you received my email message, you know already that this material that I am going to cover this week is not going to be on the midterm. However, it will be on the final. And it's a very important material. It really sets the stage for the next half of the course because as it says here, we're going to start looking at the first law of thermodynamics for a control volume, which remember that means also that this is an open system. So it means that mass will now be allowed to cross the boundary of the system. In all of the problems that we have done so far, the system was closed. So all of the mass was inside the cylinder or inside the tank. In a couple of problems, maybe it was moving from one tank to another tank or from one tank to a cylinder. But you could, in all those cases, still consider your mass as a whole and therefore call it the system and refer to it as a closed system. But if we're dealing with a control volume, and therefore we are going to allow for mass to cross the boundary, we must now, in addition to keeping track of the energy, which is what we do with the first law of thermodynamics, we now need to keep track of the mass. And the situation could be as simple as this, for example. Let's say you have a tank, like the ones we have seen before, but this particular tank has two openings. It has an inlet and it has an outlet, and there is mass coming in through the inlet and mass leaving the system through the outlet. So if I pick the boundary of the system to be the dashed line that you see there, then that is an open system or a control volume, because there is two places where mass is crossing the dashed line, at the inlet once and then once at the outlet. So that's essentially the type of problem that we want to be looking at. So mass conservation, which is the way we keep track of mass, is actually very simple, because if we keep track of mass in this situation, it's not very hard to come up with the equation that you see right there in the box. For example, I could keep track of the mass change inside the control volume. And then, for example, think of the process the way we have been looking at them. So there is an initial state and a final state. So I could look at how much mass was inside the control volume at the initial state, and that would be M1. And I could look at how much mass was inside the control volume at the end state, M2, and just compute the difference, M2 minus M1, which is my delta M in the control volume. And if you do a very simple mass balance, you find out that if there is indeed a difference between those two, it has to be due to the fact that mass came in and mass went out. So the total change of mass inside the control volume is going to be equal to the difference in the amount of net mass addition. So M in positive and M out negative. So that's fairly simple. But what this does for us, for example, is that now we can look at, you have here an example of a tank with an inlet and an outlet. But we can actually look at something that starts to make a little bit more sense from the engineering point of view. For example, here is a schematic that I showed you during the first lecture of a power plant. So this power plant is there to deliver a certain amount of power to us, net power out. But the way it does that is by having all of these other devices as part of the power plant. So this is a simple schematic of a power plant. It has really four main devices. It has a so-called combustor unit up here, where fuel is mixed with air, for example. burned, produce high temperature combustion products, and then that high temperature is used to create steam. So high temperature, high pressure water. And then that high temperature, high pressure steam is then used to drive a turbine. The turbine delivers the net power out that we want, and then the steam comes out from the turbine at a lower pressure. But then in order to complete the cycle, you need to turn that steam back into liquid. That brings in the third component, which is this condenser. In the condenser, you might use a cooling water. You need to have a supply of cold water nearby, which is why you would see most power plants built near where there is a large supply of water, like near the ocean or near a lake or near a river. And then by taking the energy out of the steam in the condenser, you turn it into liquid. And then the fourth ingredient, the fourth component, is a pump, or several pumps, that we now take this liquid that comes out of the condenser and pump it up to the pressure that is needed to put it into the boiler, into the combustion unit, and that closes the cycle. So there are several ways we can look at this. In order to look at this as a closed system, as far as the working fluid here, you would have to consider all components together. But if you look at each of the components separately, for example, take this turbine and think of it the same way as I did this tank, where there is a boundary that coincides, say, with the inner lining of that turbine, then that volume that we chose as the control volume is an open system. There is mass coming in, which is the high temperature steam coming into the turbine, and there is mass coming out, which is the low pressure steam coming out of the turbine. So we can look at all of those separately. When we look at a process such as this, we refer to it as a Rankine cycle. So, and you will look at Rankine cycles in more detail later. But here are the four components, the four devices that we were just looking at: the boiler, the turbine, the condenser, and the pump, just like you saw them here. Boiler, turbine, condenser, and pump. But now I am sketching them so that I can look at a property diagram. And also because this way I can label inlet and outlet states. So I have labeled 1, 2, 3, and 4, as you can see here. 1 being the place where the liquid goes into the boiler, 2 as it comes out of the boiler and goes into the turbine, and then 3 after the turbine, before the condenser, and 4 after the condenser and before the pump. So this is sort of a very simplified version of what this power cycle would look like. And if I now try to put these states 1, 2, 3, and 4 on a PV diagram, then it might look something like we see here at the bottom. So pressure on the vertical axis, specific volume on the horizontal axis, and my 1, 2, 3, and 4. Notice, for example, if we start from 1, I said that's the high pressure liquid that goes into the boiler, and indeed 1 is at a high pressure, compared, say, to 4. And it's going into the boiler. It's a compressed liquid. So it is a liquid. Goes through the boiler, and you can see in the Rankine cycle how that process is a constant pressure process. So as you go through the boiler in the thermodynamical sense, it is an isobaric process. So it comes out at 2 as it goes all across the dome and in fact gets superheated. Now we have a superheated vapor that is coming out of this boiler. Then it goes through the turbine, comes in as a high pressure superheated vapor. It may come out as still as a superheated vapor, but at a much lower pressure. Right? So the pressure here at the bottom is lower. And then that liquid, that vapor, the slightly superheated vapor, as you can see here in 3, is put through the condenser. It will typically come out as compressed liquid 4. Or in a simplified scenario, it may also come back as saturated liquid right on the dome line. And then again, going through the pump from 4 to 1, we have a liquid, and all we're doing is increasing the pressure from the low pressure to the high pressure. So this is a simple Rankine cycle. So we can label this pressure here the low pressure, and then label this pressure here as the high pressure. And that's how we think of a Rankine cycle, as operating between two pressures: the high pressure, which is the pressure in the boiler, and the low pressure, which is the pressure in the condenser. All right? So our goal then in this chapter is to analyze, to be able to analyze each one of these components and determine some quantity that is important for us to determine. For example, I may want to know how much heat I need to add into the boiler so that I indeed come out at state 2 where I want state 2 to be. Or I may need to find out how much heat I need to remove in the condenser so I can indeed come out at state 4. Obviously, the most important quantity perhaps is the power that comes out of the turbine. Notice that it is also usually a much smaller amount of power that is needed to drive the pump. So all those are quantities that we should be able to calculate after we go through this chapter. So that's one type of problem. Another type of problem that we will be able to do is a problem like this. We have seen some variations of this problem. I remember looking at a problem where there was a line carrying something, and but in this case, the situation is slightly different because what I have here is a tank that, as it says here, is initially evacuated. So there is nothing in here. It's an empty tank at the beginning of the process. And then what we have is we have this line, this pipe that is carrying a substance at some constant pressure and temperature. And then this valve that allows for that substance to flow into the tank. So by opening the valve, then I can allow for this fluid that is going through this line to come into the tank, and I can determine things that might be important to me. For example, find out what the final state of this gas or liquid is after the tank is filled and I close the valve. Things like that. So there are these two types of problems, and we're going to look at them in detail. Problems like this one, we were just looking at, for example, take this turbine, which we will look at them when the turbine is operated in the so-called steady state conditions. That is, the turbine or the condenser, the pump or the boiler or whatever the device is operating in steady conditions. That means it's continuously running at some speed. You know, if it's the turbine, it's rotating at some speed. And the fluid is coming in at the inlet port and coming out at the outlet port, always at that same continuous rate. Those are the so-called steady state problems. And then there are these problems where clearly the situation is not the same at all times. So for example, if I look initially at this tank, it is empty. If I look halfway through the process, then it's a little fuller. And then if I keep going forward in time, then I get more and more mass. So this is an unsteady situation. The state within my control volume is changing in time. Whereas to re-emphasize in a problem like this, if I'm looking at the turbine, I will look at the turbine as it is continuously running in steady operation. Those are the two types of problems that we're going to be looking at. So let me go back to this equation, the equation that tells me how much the mass inside the control volume changed. And suppose that I want to convert this equation to a rate type of equation. So we talked a little bit about this last time when we were looking at the rate form of the equation. So this applies, for example, I could be looking at a process that starts at 1 and goes to 2. Any two properties. So I have a certain amount of mass here at M2 and another certain amount of mass here at M1. And this equation would measure the total variation of mass at 2 versus the initial value at M. But I could also just look at a small portion of that process. So this red segment is just a small portion of the entire process that goes from 1 to 2. And I might be interested in knowing how much the mass changes inside the control volume during that infinitesimal segment of the process. And instead of calling that delta M, then I would call it dm. That would be, and let's be specific by saying in the control volume. So I'm looking at the same control volume, but now I am just looking at the variation over an infinitesimal amount of time. And of course, applying the same calculations here, now I would have, of course, only an infinitesimal amount of mass coming in. So I would say dm in, and then an infinitesimal amount of mass going out. So it's the same equation, but instead of being a delta m, it's a dm. And instead of dealing with total mass in and total mass out, I'm talking about a differential amount. So if I now divide by time, so if I take this and divide by dt, which is whatever time elapsed as I went from the beginning of that rect segment to the end of that rect segment, then this is what I have. So then I leave this just like that. dm cv dt is just telling me the rate at which mass is changing during that infinitesimal amount of time. And then I just relabel this like we did last time for the energy. I call this m dots. So I say this is going to be m dot in, the rate of mass going in, and this is going to be m dot out, the rate of mass going out. And I end up with this equation. So dm cv dt equals m dot in minus m dot out. And that's also my conservation of mass equation, but it's in the so-called rate form. It's measuring rates of mass change. Of course, the units would be in kilograms per second, as opposed to the original equation, where the units would just be mass. So these two are equivalent expressions of mass conservation. One is in the so-called before and after form, beginning to end, and the other one is just an instantaneous rate of variation. So that's how we keep track of mass conservation. Raise your hand if you happen to have a question. Now, there is another thing that we have to worry about because of the fact that there is mass going into a control volume and mass going out of a control volume. So let me show you this picture here. And this is a very generic description of a control volume. So there is my control volume. It's inside this control surface, which is the dashed line. So the dashed line represents the control surface. And notice that I have also sketched here what is to represent a certain amount of mass that is going to be pushed into the control volume. So clearly what we're trying to do is look at the details of how mass flows in or out of a control volume. So I sketch it as a little stocky cylinder. That's the mass that I'm trying to push in. So whatever is inside here, this stocky cylinder, is the mass that I'm pushing in. So, and there is a force outside, dF. It's a differential force because it's a differential amount of mass that is pushing this in. So the little stocky cylinder has a total height of dx, and it has a cross-sectional area of dA. So what does it take to push that in there? Well, let's look at some things. The volume of the stocky cylinder that has the mass that is going in is obviously simply the product of dA times dx. That's a differential volume that is going to enter the control volume, that is going to be pushed into the control volume. If I want to write it down in terms of the rate at which it goes in, then I just divide by dt. So I take that dV, divide by dt. So I get dA dx over dt. But of course, dx dt is nothing but the velocity, because dx was the length normal to the surface, is the velocity at which it is being pushed in. And I call that v sub n. The n is because it's normal to the surface. I'm pushing it normal to the surface, dA. All right? So I have that. Vn, velocity normal to dA. So of course now I can do the mass flow rate by simply multiplying the previous quantity times the density. So if I just take the dV dt that I just computed and I multiply times the density, which is the same as dividing by the specific volume of the stocky cylinder, then I have an expression that tells me the dm dot that we were just looking at in the previous equation. When I wrote the equation, when I wrote the equation as a differential mass, dm, what I have is now what I can call dm dot. Is the differential mass going in. So it's simply 1 over the specific volume times dV dt. And finally, if I write dV dt in terms of what I found earlier, so I found that dV dt is just the area times the normal velocity, then I come up with this expression. That the rate at which mass is being pushed in, called dm dot, is equal to either I can write it as the product of rho times the area that the mass is crossing times the velocity, or if I write it in terms of the specific volume, it's just 1 over v times dA times v. That's a very handy expression. It always allows you to find the mass flow rate if you know the normal cross-sectional area, the velocity normal to that surface, and the density, or the specific volume. And we're going to use it. Just want to derive it there, leave it there, and use it in a little bit. So I can compute this mass flow rate. Now, what is needed to push this mass inside this control volume? I need a force, but that's not enough. What else is needed? It's due to the force.
Pressure?
No, well, the force would be pressure times some area.
Acceleration?
Sure, it has to move, but there's another quantity that is more important to us. Whoever is outside pushing this mass in is doing what? Work. Right? So to push this mass into the control volume, the surroundings, because remember this, all we have is system, boundary, and surroundings. The surroundings are doing work to push that mass in. You can also think of the opposite situation. Suppose instead of being pushing the mass in, we're pushing some mass out. Then now the system has to do work to push that mass out. So that is clear. There will be work needed done by the surroundings if the mass is going in, or work needed done by the system if the mass is going out. So let's calculate that amount of work. So we give it a name. We call it flow work. Just because it is the amount of work that is needed to flow that mass represented by the stocky cylinder into the control volume. So flow work is the work done by that force dF to push the volume through the control surface. CS is the control surface. Okay, so how much work do I need? What will be the work needed to completely push this red cylinder into the control volume? Say that again. dF times dx, right? It's the force times the displacement. We don't have to worry about integrals because it's all differential quantities. So that work is just dF dx. And like you said, you brought up pressure a moment ago. I can write, of course, the dF as the product of the pressure times the area. So I can write dF is PdA, so I can write PdA dx. But of course, dA dx, we saw it earlier, was dV. It's the volume of the mass that I am pushing in. So it turns out that the surroundings have to do an amount of work, delta W, which is equal to P dV. The pressure times the volume of the mass that is being pushed in. And if I want to look at it in terms of rate again, all I need to do is divide by dt. So if I now divide by dt and call it delta W dot, which is just delta W over dt, well, that will be P dV dt. But of course, earlier we had seen that we can write dV dt in terms of the dm dot as specific volume times dm dot. So now I have two handy expressions. One here that tells me how to calculate the rate at which the mass is going in, kilograms per second. And I have another one here that allows me to calculate the amount of work needed to push that mass in. Pressure, specific volume, times the mass flow rate itself. So this is the so-called flow work. So we put it in a box nicely so that we can remember it. The flow work is P times V, specific volume, times the mass flow rate. All right. So now we have a way to measure in mass, in and out, and the mass variation inside the control volume in terms of totals and also in terms of rates. And we have a way to calculate the work that is needed to push that mass in and that mass out. So now we're ready to tackle the first law and see what will happen to the first law because of this new possibility of mass crossing the boundary. Here is our old first law. First law for a closed system that we have been looking at for the last couple of weeks. So CM, control mass, and there it is. The change, the time variation of energy inside my controlled mass or inside my closed system is equal to the rate at which heat transfer is occurring minus the rate at which work is being done, with the sign convention in mind. That's why the work appears negative. And that's the rate form. Right? So I already wrote it in rate form because that's what I will need for what I want to do next. Now the question is, this was the first law for a closed system. Is this going to change when I am dealing with an open system? You think this will have to change? Yes. And how will it change? Who said yes? How will it change?
You're going to have to add the rate of workflow as part of your energy.
And the what?
As part of your energy.
Yeah, so what we just did, we were calculating that work. That somehow will have to come into this picture. The work that was done by the surroundings or by the system to push mass in or out. Is there anything else that will have to come in to the picture besides that work, that flow work? When mass comes into a system,
Mass that goes out.
and mass goes out of the system, is there anything that we should consider?
The change of mass.
Well, but that's in the mass conservation equation we just did. This is an energy equation. In terms of the energy equation, is there anything else that we should consider?
Maybe the heat from the flow of the fluid.
Okay, it's not really the heat of the flow, but I think you're going in the right direction. That energy.
Is it the internal energy that's leaving?
Well, okay, yeah, I didn't mean to say that energy. That mass has energy. Internal energy for the most part, but it may also have kinetic energy, it may have potential energy. So the mass that goes into the system, this mass that goes into the control volume, onto the open system, has energy. Every piece of mass has energy. So when that mass goes in, it brings in energy. or if it goes out, it takes energy away. So we have to take that into account. Energy that comes in with the mass that comes in, or energy that leaves the system with the mass that leaves the system, plus the flow work. So these are my questions, right? So this needs to be modified. How, why? We already answered all of that. Mass crossing the control surface, system bound, so going inside carries energy with it. So let's put some symbols to this. So E dot control surface, right? The mass that is crossing the control surface has some energy, carries an energy rate, capital E dot, which of course will be the mass flow rate times the specific energy that that mass has. And like I said, for the most part, that E, lowercase e, is really lowercase u, internal energy. But there could be kinetic energy, there could be potential energy. So we do it, of course, separately. So we write a term for the mass that is going in and a separate term for the mass that is going out. So we take this equation then, we take this equation and add all these things. And what do we end up with? Let me actually just show you this. We don't really need all of this writing here. Here's the equation. All right, let me make it a little bigger. And hopefully still fit it in there. Okay, so here is the original equation. It only had two terms on the right-hand side, the heat transfer rate and the work rate, or the power. All this that is here on above the red line are the new terms. So it seems like a lot of complicated things, but it's not really if you think about what we just said. So here you have m dot I E sub I. That's energy carried in with the mass that goes in. This is lowercase, so it's per unit mass, so I need to multiply times m dot, subscript I for inlet. So I add that term. And then, of course, I subtract the equivalent term for the mass that is going out of the system. So I have a minus m dot E times lowercase e sub E. That's the energy in and energy out carried by the mass in and out. And now I have the flow work terms that we were just looking at. So the amount of work that is done by the surroundings to push the mass in, and the amount of work that is done by the system to push the mass out. So one is positive for the one coming in, and the other one is negative because it's going out. When the system does the work, it uses energy.
So if like the problem we're looking at where you're pushing something in, there would be no ME terms. There would be, because there's nothing actually.
Are you talking about the tank?
Or just the one where we were just like.
Yeah, so like this example. Yeah, in this example, obviously there is nothing going out, because all I have is this one valve and there is flow going in. So there will be problems in which there is nothing going in, problems in which there is nothing going out, and problems, of course, in which there is both mass going in and mass going out. If you think of the turbine, or if you think of this original sketch for this tank, there is in and out. So now what you have to do is, once you understand this equation, then you can adapt it to your problem. But that's the full equation, and that's the first law. Now, this can be simplified a little bit. How do we do it? Well, you remember enthalpy. So let's use enthalpy, the definition of enthalpy, to combine some of the terms. See, for example, what you have here. You have m dot I E sub I, and then over here you have plus m dot I P sub I V sub I. I'm going to combine those two together by first remembering that this lowercase e is total energy per unit mass, and it's made up of internal, kinetic, potential, and anything else that that mass may have. So if I take then those two terms, so this term and this term and write them separately out here, I can factor out the m dot I, that is the E sub I, plus pi vi, and then break down the E sub I into U sub I plus kinetic energy sub I plus potential energy sub I plus any other form of energy sub I, and then there is the plus pi vi. And now I just take the internal energy, part of the equation. Let me move this a little bit. Take the internal energy and add it together with pi vi to form enthalpy. So we know that enthalpy, let me shrink this again so we can see it in one page. We know that enthalpy, for example, H sub I will be U sub I plus pi vi. That's the enthalpy of the incoming mass. So I can take those terms, MIEI plus MIPI-VI, and write it like this. Enthalpy, kinetic energy, potential energy, other forms of energy. You might say, well, that didn't really accomplish a whole lot. Right? Essentially what I did is I eliminated one term, right? Because I had, this has all of these, U, kinetic, potential, and others, and then the PI-VI. That's really the only one I got rid of, the PI-VI, because it is no longer here. It's absorbing this H. So this H has the U term and the PI-VI term. That's all we did. We just got rid of one term. However, what happens in a problem in which you neglect all the other forms of energy, which we do a lot. Right? Many of our problems, this kinetic energy, this potential energy, and these other forms of energy can be neglected compared with the enthalpy. So then you can say, well, now we accomplished something, because all we have then is one term left on the right-hand side for that mass that comes in, and another one, of course, for the mass that comes out. So here's the full equation. This is the same equation. So this is just the same thing written in a little cleaner way. The old form of the equation is still there, and everything here on the right-hand side that has the m dots is new. I broke it into two lines so it's a little clearer. So m dot in enthalpy, kinetic energy, potential energy, other forms of energy. Same thing for the out. So now you can see if I neglect variations in kinetic energy, potential energy, and other forms of energy, then I have an equation that is a lot. Now you can see that it's simpler. So it started looking really bad, but if you make those assumptions, so maybe I should keep that here, because that's important. The conditions for using this equation is neglect kinetic energy, potential energy, and other forms of energy. All you have is for the mass that flows in is you need the enthalpy of the flow going in, and then you need the enthalpy of the flow going out, the exiting enthalpy. Notice that I also changed the left-hand side. In the original equation is a dE dt, but because I am neglecting kinetic energy, potential energy, all I have left on the left-hand side is internal energy. This is the most comprehensive form of the first law of thermodynamics that we are going to have in the class for a control volume. Make sure you understand what everything means. Right? So this left-hand side is the time variation of the internal energy inside the control volume, and then everything on the right-hand side, is energy forms that are crossing in or out. Heat transfer, work, and mass, flowing in or flowing out. Right? If nothing is happening, of course, if there is no heat transfer, no work, no mass going in, no mass going out, the conclusion is obvious. The internal energy of the inside the control volume should be constant, should not change in time, because nothing is being added or subtracted. So everything on the right-hand side makes a change in the internal energy inside the control volume. Okay, any questions? All right, so let's look at the two types of problems that I was telling you about. this is, or these are the two types of problems that we're going to study. I already mentioned them to you. The so-called steady state processes and the so-called transient processes. So remember, the steady state process, I used the example of the turbine in the Rankine cycle, is, for example, to think that this plant is operating continuously. If you're, for example, analyzing the turbine, then there is a continuous flow rate of vapor going into that turbine, a continuous flow of vapor going out of that turbine, and a continuous production of power out of that turbine. It's all operating in, that's what we refer to as steady state. It's happening continuously, not changing in time. And the other type is the so-called transient process, which you were just asking about, which an example, a simple example is filling up a tank. That's a process where the conditions are changing in time. So, and we look at them in a slightly different way. So I want to go over them carefully. Let's look at the steady state first. And then the next lecture we'll look at the unsteady ones. So in the steady state, what happens? Remember, the key is that the process occurs continuously and does not change in time. If the process doesn't change in time, then I can say that the mass inside the control volume is always the same amount, and the energy inside the control volume is always the same amount. What does that do for me? If these statements inside this red box are true, what happens to my equations? You agree with this? The rate of change of mass inside the control volume has to be identically equal to 0. And the rate of change of energy inside the control volume, the time rate of change, has to be identically 0. That's the meaning of steady state. You look inside the control volume, nothing is changing. Well, that's a nice simplification, because if you're looking at, say you're looking at this equation, the last one we were looking at, now I can just put a big 0 on the left-hand side. Okay? No changes inside. That means that everything else on the right-hand side has to balance out to give 0. That's the typical feature of a steady state problem. So we start by saying that there is no variation of mass in time inside the control volume, no variation of energy with time inside the control volume. The type of devices that we're going to look at, you saw some of them in the Rankine cycle diagram, but here I made a list of a few that where we'll probably focus most of our energy here. Heat exchangers. A typical heat exchanger, for example, is the condenser that we were looking at. I lost my Rankine cycle figure. Oh, here it is. So the condenser here, this is a heat exchanger. It's essentially exchanging heat. It's transferring heat from the steam that came out of the turbine into the cooling water that comes from your water supply. So the cooling water gets in and comes out warmer because it's taking that heat away. That's a typical heat exchanger, a condenser. Other heat exchangers, for example, are evaporators. They do the opposite. Instead of condensing, the idea is to evaporate. Turbines to produce power. Pumps to increase pressure. Compressors also to increase pressure. What's the difference between a pump and a compressor? Both are there to increase pressure. Liquid versus gases, right? So pump with liquids, compressors with gas. We'll also look at nozzles. Nozzle is designed to increase the kinetic energy of a flow. this is a case where we might not be able, in fact, we should not neglect the kinetic energy that we neglect in many other problems, because the idea of a nozzle is to increase kinetic energy, increase the velocity of the fluid. The diffuser will do the opposite, reduce kinetic energy, slow down the flow. So those are two scenarios, nozzles and diffusers, where we have to go back and use the full equation at least to retain the kinetic energy, because if we just use this one, we have neglected kinetic energy. So in a case like that, we have to come back and keep that term in, kinetic energy, if we're looking at a nozzle or a diffuser. All right, so what happens to conservation of mass? Once we put the left-hand side to 0, then of course the right-hand side of conservation of mass had m dot in minus m dot out, or exiting. Of course, what that tells me is that I must have the same flow rate coming in as I have coming out. Otherwise, it will be impossible to have the same mass inside the control volume. So if I go back to my original example, if this is operating in steady state, this tank, that means that the mass in here cannot change in time, then m in must be equal to m out. That's very obvious. And then, of course, there is the first law. So if I look at the first law in a problem in which the flow is steady, then I can just go ahead and cross this, du dt. All right? Any hands up? Let me do an example. By the way, if you look in the book, this is just a summary of devices, but there is a table in the book where you have a lot more devices. And I just put red arrows on the ones that are more important for us, or that we'll use more in the class. But there's another nice thing about this table. It helps you understand the device. It tells you what it does. So for example, if you pick the nozzle again, it tells you that the idea is to create kinetic energy. So increase kinetic energy. It says that normally the pressure will drop. But it also tells you other assumptions or conditions that you can assume for those devices. In the case of a nozzle, it tells you no work, W equals 0. It also tells you no heat transfer. Assume that those are 0 when you're working with those devices. It doesn't mean that those givens or assumptions are always true 100% of the time, but most of the time you can work with those assumptions when you're working with those devices. So I picked one to do an example. I picked a mixing chamber. So if we look at a mixing chamber here, we see that it says mix 2 or more flows, and no work, no heat transfer. Okay? So let's look at an example of that. So it would be something like this, like the one on top there. It's a type of a heat exchanger. So for example, I could be taking 2 streams, one here, mixing them and producing a new stream out. That's a simple mixing chamber. This schematic also has a few other heat exchangers. Other types of heat exchangers. This is the so-called counterflow heat exchanger. One fluid is going through this tube, and the other one is going through the shell around the tube, but it's counterflowing. So the one in the tube is going from right to left, the one in the shell is going from left to right. Comes in here, comes out there. This is the same but co-flowing. They're both flowing in the same direction. They're not mixing. So in the mixing chamber, you're mixing the fluids. In a heat exchanger like this or like this one, you're not. And then here's another one, which is pretty much like the radiator in your car. So where there is a fluid going through maybe the coils and another one going through across. Okay, so here's my mixing chamber example. we have the following. Okay, so we start here. Here's my mixing chamber. It's just a rigid tank. It has one inlet, and it has two inlets. 1 and 2 are inlets, and 3 is an outlet. I'm told that it operates in steady state, so I know I can use the steady state form of the equations. I'm told it's insulated. That means what? I'm sorry? Yeah, no heat goes in or out. So that has to do, if you look at the table before that I show you, when you look at mixing chambers, it says Q equals 0, no heat transfer. So that's an assumption. That's not always true. I could have a mixing chamber that gains or loses heat to the surroundings. But let's assume that it is insulated. It has the two inlets that I mentioned, 1 and 2, and an outlet 3. And then we're given the conditions of the inlets and the outlets. So we know at the inlet, number 1, it is saturated liquid coming in. This is water. So water as saturated liquid is coming in at a certain temperature, 90 degrees Celsius, and a certain mass flow rate, 5 kilograms per second. And then the purpose of the tank is to take this saturated liquid and deliver it at 3 as saturated vapor. So what we want is to take the saturated liquid from one end and deliver it at the other end as saturated vapor at the same temperature, 90 degrees Celsius. And the way we're doing that is by bringing in superheated vapor at 2, which is at a high pressure of 300 kilopascals and at a high temperature of 500 Celsius, bring it in into the tank, mixing it with the liquid to produce the to produce the saturated vapor. So obviously the key design question is, what is the needed mass flow rate of superheated vapor to produce the saturated vapor? So how much should I flow in through 2 so that I can get what I want at 3, which is saturated vapor? That's essentially what the problem is about. So how do I solve it? Well, first thing we can do, of course, is get the data. So by now, of course, it means that you can quickly get all this data. With this temperature and knowing that it is saturated liquid, we can get data for state 1, no problem. Regarding the added superheated vapor, we have pressure and temperature, so again, no problem. We can go to the table and get the data there. And we want saturated vapor at the outlet 3 at a temperature of 90 degrees Celsius. That's also completely specified. So I can go to the tables and get any data that I want for these 3 conditions. Which data do you think we should get from the table? So here is the, let's take the inlet 1. Here is the saturated water table. Temperatures, pressures, VF, VFG, VG, you know the story, UF, UFG, UG. There's something new now. We have only so far looked at the left side of the book, of the table, when we look at a table like this, but it has a right-hand side. And you look, when you open the book, it actually has 2 sides like this. So it's the same table, it just keeps going. If you keep going to the right side, it repeats the temperature and pressure, so you don't have to go all the way across. But now it has enthalpy, H of F, H sub F G, H sub G, and then some entropy, which we haven't even gotten into. But of course now, as you saw in the first law for an open system, enthalpy is important. So what do you think I should read from here? When I go to the table, say the state 1 is 90 Celsius. So that's this line. Right? You cannot see the 90. Well, you can see it on the other side. What should I read?
HF. Because it says it's a saturated liquid at 90 degrees.
HF. What else should I read? What else should I read? Somebody from this side. He's saying read HF. What else should I read? Huh? You guys are consulting with each other. What's the consensus? What else should we read?
HG for the end state.
Yeah, HG. I should read HG. Should I read use?
If you read the pressure.
Should I read use? UF, I'm sorry, right here. UFs, UGs. Should I read those? The answer is no. You'll see why. So I can get those from there, and I can then go to the superheated table and read for my 2 state, 300 kilopascals, 500 Celsius. This is 300 kilopascals, 500 Celsius. Read H. All right? Take that H. So we can do that and then write it all down. And that's all you need to read. So go through the tables. B11 to read H1. This is the HF. Right? The HF. Maybe I'll put it here. This is the HF at 90 Celsius. H sub 2 is the superheated steam. That's just H, read in table B13, superheated. That's just H. And then state 3, again back to B11. This is H sub G, also at 90 Celsius. So I can get all of that. So I have all those numbers. Why is it that I don't need any other numbers? Well, we'll see when we look at the equation. But the first thing would be to say, well, let's look at mass conservation. There is my mass conservation equation. Right? How will this equation simplify for my problem? Tell me what I can do with this equation. Well, maybe don't tell me that, but can I simplify it?
For the left, equals 0.
Left-hand side is 0, all right? So I can cross out the left-hand side because I'm looking at this mixing tank in steady state. So big 0 on the left-hand side, no changes in time. And then what about the right-hand side? Notice that it says the sum of all mass flow rates in. So I need to consider all of the mass flow rates in. And if we go back to the sketch, those would be 1 and 2. Right? So I can just simply write for the sum of everything going in is m dot 1 plus m dot 2, and then minus the sum of all the mass going out. But there is only one place where mass is going out, and that's at 3, so I just need to write minus m dot 3. This equation, you might argue, well, this was very obvious to me because all you're saying is that m dot 3 is m dot 1 plus m dot 2. You could have said that without knowing a lot of thermodynamics, right? The two mass flow rates that come in at 1 and 2 get added and produce mass flow rate number 3. But you got to go through the exercise sometimes if you don't see it right away. So that's my mass equation. And then what about my energy equation? Here is the full equation. Okay, there is the first law. Notice that I have only included enthalpy terms on the right-hand side. So I have neglected kinetic energy, potential energy on the right-hand side. Well, even though I didn't do it on the left-hand side because I left the E. I didn't change it to a U. But in this problem, again, this is not an issue because what happens to the left-hand side? This is 0. It's a steady flow problem, so there is no time variation. What about Q dot? 0 because we were told the tank is insulated. And what about W dot? 0 because it is a rigid tank. So all of that is 0. And therefore all I have left is the sum of the mass flow rates times the enthalpies at the inlet minus the mass flow rate. So I can just simply write m dot 1 H1 plus m dot 2 H2, those are the inlet, minus for the outlet m dot 3h3. All right? So what's known and what is not known here? M dot 1 was given. It was the flow rate of liquid, which was, I think, 5 kilograms per second. So that is given. H1 we read in a table. M2 is our unknown. H2 we read in a table. M dot 3 is, according to mass conservation, equal to this, right? Of which the first one is known, and the second one is our same unknown, and then H3 is known. So the only unknown in this equation is m dot 2, okay? Which of course I can go through the little exercise, write it like that, m dot 1 H1 plus m dot 2 H2 equals m dot 3 H3. That's the same as that equation. Then substitute in the fact that m dot 3 is m1 plus m2. Put that in there and then bring all the m2 to one side. So whatever has an m dot 2, because that's my unknown, I'm going to bring to the left-hand side. It will be a factor of H2 minus H3, and the rest I leave on the right-hand side. That's m dot 1, factor of H3 minus H1. The rest is just simplifying this. So solve for m dot 2. And then you get this expression, which essentially, since you know all the enthalpies, will tell you the ratio of m dot 2 over m dot 1. You know, per kilogram of liquid, how much superheated steam do you need? If you plug in the numbers for the enthalpies that we pulled out of the table, you find that that factor is 2.76. So you need 2.76 kilograms of superheated vapor per kilogram of saturated liquid that you want to convert to saturated vapor. And if you plug in the 5 kilograms, then you get that you need 13.8 kilograms per second of superheated steam to come in here at 2 to produce, of course, 13.8 plus 5, 18.8 kilograms per second of saturated vapor coming out at 3, because everything out is going to be saturated vapor. If you put it, in a diagram, then you don't really know exactly how the mixing takes place, but I could do a PV diagram, and all I can do in this diagram is put all the states that there's my red. So whatever the pressure is at 90 Celsius, that pressure is 70.1 kilopascals. So this is 70.1. This is in kilopascals. And I know that this is what went into this is 1 that went into the mixing chamber. 3, remember, was superheated somewhere over here at some high. No, I'm sorry, 3. This is 2. Yeah, thank you. 2 is the superheated vapor that I'm using to produce saturated vapor at 3. So those are all the states at the inlets and outlets. So 1 and 2 are inlets, 3 are outlets. We don't really need to join them in any way because particularly we don't know exactly the process that 2 went to go out to 3. This is maybe more obvious that it had to go across like that. But at least you can put on a PV diagram all the states of all of the inlets and outlets. Okay, any questions? Okay, let me just then ask you a couple of questions to finish today. That's from last time. So that's just for you to get ready. Okay, so if you're ready, I have 2 questions, I think, for today. Here's the first one. I am giving you there 4 forms, possible forms of the ideal gas law. Tell me if there is one there that is not correct. Okay, so 5, 4, 3, 2, 1, 0. Okay. Which one is not correct? You said mostly D. P equals rho RT. If D is not correct, right, then C would not be correct, right? If D is not correct, then D would not be correct because rho is m over v. So you want to change, those who said D, you want to change that? What do you change it to? B? Well, little v is capital V over m. So if C is correct, then B is correct. So when you want to change it? Answer is E. Those 4 expressions of the ideal gas law are correct. A, B, C, and D are all correct. All right? Okay. Do another one. Okay. Here you have a cylinder, piston, spring system. You want to calculate the work for this. Suppose there is a process and this piston moves either up or down, it doesn't matter. And you want to calculate the work. Is it A, B, C, D, or E again? Okay. 5, 4, 3, 2, 1. Oh, there are more answers this time. Some people didn't answer the first one. Okay, and then what do we have? Wow, that's a pretty resounding majority. So C, which is a half m P1 plus P2, V2, V1, that is correct. So the yellows have it. That is correct. And then if you don't know why, try to find out why. Okay. So the next question would be, why is it that one? Okay, for example, why is it not A? Because A is for a constant pressure process at P1. So if there was a constant pressure process at P1, then A is the right answer. B, we haven't seen anything like that because it's like a V delta P. There is something like that coming up later, but not for this type of a problem. So it's either C or D. You need to ask yourselves the questions as to why is it a minus and not a plus. All right, so I will not see you on Thursday, but the lecture will be uploaded, and we'll meet again a week from today.